Hello friends, this is my next video about AC fundamentals. In my last video, I have told you about all the concept related to DC, that what is DC voltage, what is DC current, and what is the direction of DC current. But in this video, we will see all the AC fundamentals, all the concept related to AC. I have divided this video in 5 topics. First is difference between DC and AC. Then frequency. Then we will see the mathematical representation of voltage and current in AC. Then we will see what is peak voltage, what is peak to peak voltage and current. Then we will move on to know what is RMS and what is average values. So friends, let's now move on with the difference between DC and AC with the first point. In my last video, I have told you about DC, that DC is a direct current, AC is alternate current. In DC, voltage and current remain constant throughout the time. Means if this is my y-axis, which is voltage, and this is my x-axis, which is time, then the voltage will remain constant throughout the time. It will not go below zero. That means if this voltage level is 5 volt, then it will remain 5 volt throughout the time. But it's not the case in AC. If we draw a voltage and time graph like this, then in AC voltage will first go positive, then go negative. Again it repeats its cycle. This is AC. Here voltage level first go to the positive, then goes to the negative. This is called alternate cycles. This is positive and this is negative. Again it will go positive and again it will go negative, and it repeats itself. DC can also be represented like this waveform. It looks same as a sine wave, but actually it is a DC. Why it's DC? Because voltage level is not crossing this zero line, this value 0. It is not going negative, it is remaining positive. Yes, this value changes as it is sinusoidal wave. The instantaneous value with respect to time changes, but it doesn't alters like in AC. In AC we can see there is positive cycle and again there is a negative cycle, but here only there is a positive cycle. Another way of representing DC means this can be also called as an DC wave. Let's see AC now. We can have waveform like this also. If we consider the triangle wave, then it is also an AC because it is changing its polarity. First it is positive, then it is negative. Then if we consider as a square wave, then this will be an AC like this. This is the basic difference between DC and AC. There are many examples of DC, means you can see batteries, then cells, which can provide a constant voltage, that is DC. We use AC in our day-to-day lives, that is in household outlets, power outlets. On your wall we get AC voltage, and there are many appliances which works on AC like fans, tube lights, bulbs, etc. AC can be generated using a AC generator. There is also a DC generator. We will see the generator part in our next video. How that AC and DC is generated, that we will see in our next video. But basically this is the difference between DC and AC. In DC voltage remains constant. In AC voltage varies. It changes its polarity at every half cycle. So let's move on to the topic of frequency. Unit for frequency is hertz. It is written as Hz. That is hertz. 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 Frequency term comes only in AC, not in DC. Frequency is zero in DC. To go in details of frequency, first let's see its definition. Frequency is number of waves repeating itself in 1 second. If we draw a diagram of an AC waveform, if this is our sine wave, this is time t, this is voltage axis, then we called it as a full wave when the wave travels from positive from here and back to here. This whole is called as a one cycle, that is one wave. The time period, the time it takes, the time that wave takes to travel whole cycle is called as a time period. That is time, it is from here to here. This is time period of a whole cycle. So frequency have a formula, F is equal to 1 upon T, where T is time period. Frequency, to know frequency, if we consider this whole time as a 1 second, if we consider this time as 1 second, then number of waves coming in that 1 second means if there are 10 waves, for example 4 waves, this is first wave, this is second wave, this is third wave, and this is fourth wave. If we have a 4 waves in 1 second, then it is called as a 4 hertz. Same way, if we have 50 waves in 1 second of period of time, then it is called as a 50 hertz, and so on. Here frequency and time is inversely proportional. Suppose we take an example where time period means this wave, time period of this wave is of 20 millisecond. Then according to the formula, frequency will be 1 upon 20 millisecond, that is equal to 50 hertz. What does that 50 hertz means? In 1 second there are 50 waves of 20 milliseconds time interval. This is the concept of frequency. So depending upon number of waves in 1 second, frequency increases or decreases. Suppose we have 10 waves in 1 second, then it is called as a 10 hertz wave. Wave with a frequency of 10 hertz. If there are 50 waves in 1 second, then it is called as a 50 hertz wave. If there are 1000 waves in 1 second, then it is called as a 1 kilohertz wave. If there are 10 lakh waves in 1 second, then it is called as a 1 megahertz wave. So frequency goes on increasing. If we increase more waves, that is if we take 10 raised to 9 waves in 1 second, then it is 1 gigahertz. If we go on increasing with 12 waves, then it is 1 terahertz, and so on. So frequency increases from low frequency to high frequency. So depending upon the number of waves, in frequency decreases or increases. If there are less number of waves in 1 second, then it is low frequency. If there are many number of waves in 1 second, then it is called as a high frequency. So let's now see how mathematically voltage and current in AC can be represented. Suppose we have a waveform like this of AC. This is time axis, this is voltage axis. This is a peak value, maximum positive voltage. maximum voltage. This is maximum negative voltage. In terms of current, if waveform of current is like this, then this point over here is maximum positive current, which is represented as Im. This point is maximum negative current, which is minus Im. If we take a time period of this full wave, that is t, then we can find out frequency from this t. We know that formula for frequency is f is equal to 1 by t. Remember, this is a capital T and this is a small t. Why I am telling so, you will come to know when we discuss the formula for it. Representation of voltage can be given as V is equal to Vm sine omega t, and representation of current is given as I is equal to Im sine omega t. Here Vm is maximum voltage, that is this point, this Vm. This Im is maximum positive current, that is this. Sine is a nature of sinusoidal waveform. Omega is 2 pi into frequency. Why 2 pi? Because the length of a wave is 2 pi, 0, pi and 2 pi. So we are taking voltage across this, so omega is 2 pi into frequency. This time is not this time, it's not a capital T, it's a small t. This small t represents the instantaneous voltage. What is that instantaneous voltage? If we see a waveform like this, then instantaneous voltage means voltage at a particular instant. For example, if this waveform is of 1 second, okay, if this waveform is of 1 second, and if you want to calculate the voltage at suppose 10 millisecond, suppose if 10 millisecond is here, okay, if you want to measure the voltage at this 10 millisecond, that is here, you want to calculate this voltage, at that time this formula is used. There t is substituted by this 10 milliseconds. So from this formula you will get the voltage. In same way it is for current. Here Im is a maximum current, that is this one, and omega is again 2 pi into f. We can calculate this f from this t, and this time is the instantaneous current. This point is instantaneous current, this t, small t. So from this formula we can calculate V and I. This is a mathematical representation of voltage and current. From this formula we can calculate voltage, and from this formula we can calculate current. We have considered this wave as a sinusoidal wave, that's why we have put sin. So friends, till now we have saw how voltage and current can be mathematically represented. So we came to know that V, that is voltage, is equal to Vm sine omega t, where t is instantaneous voltage. Okay, instantaneous voltage means if this is a graph, this is a wave, then at every instant, means at this time, This is time axis, this is voltage axis. At this time there is a particular voltage, at this time there is a particular voltage, and at every point there is some or other voltages. Okay, so it is very much difficult to represent this whole wave in term of one number. Means we have many such points, many such instantaneous voltage. So how can we represent this whole wave in a one number? So to solve this problem we came into averaging. Averaging means, suppose if this is a waveform, we are calculating voltages at 3 points, over here and over here in positive cycle, and in negative cycle we are taking these 3 points voltages. So averaging means 1 2 3 4 5 and 6. So averaging means adding this whole instantaneous value, that is 1 plus 2 plus 3 plus 4 plus 5 plus 6, and dividing it by 6. Means in short we are taking a mean of it. We are adding whole these points, all 6 points, and dividing it by 6. So it is a averaging. The number came out of this result. Suppose if it comes as 40. Okay, then the average value, that is V average, is termed as 40.
So instead of talking in terms of instantaneous voltage, we use term as a average voltage.
So let's see what is average voltage, that is what is averaging. It is defined as the area under the waveform with respect to time. It is defined as the area of the waveform with respect to time. What does this mean? If we have a waveform like this, okay, if we have a waveform like this, if we have a triangular wave, this is time axis, this is voltage axis. Okay, this is height, this is time period. Suppose it is 2 seconds. Okay, suppose it is 2 seconds, and this height means voltage, suppose voltage be 5 volt. Okay, then according to the definition we can calculate the average voltage. V average is equal to area under waveform divided by time. Area of a waveform means this waveform is of triangular wave, divided by its time, that is 2 seconds. So in this way we can find out the average value. So this was easy, but problem comes when there is a random signal. Random signal means, suppose this is our waveform. Okay, then how will you calculate the area of it? That time it becomes more problematic. Suppose we have a waveform like this. Okay, and we have to calculate area of this. So we don't have any formula to calculate like this. So when area means when it is not a constant, when the value is not a constant, we take integration. So integrating from 0 to pi, we can find the value of this. Okay, then if we want to calculate the value of means average value of whole waveform, then we have to take limits from 0 to 2 pi, as this full wave is of 2 pi. So when area is not constant, that time we take integration. Okay, here area is not constant, so we can take integration. But integrating with respect to time means here time is from, for this wave it is 0 to pi, and this for this full wave it is 0 to 2 pi. Okay, So taking average value, calculating the average value of this positive half cycle. How to calculate it? V average means for 0 to pi. V average is equal to area of waveform upon time. Okay, that means we are integrating this value 0 to pi. We are calculating only this part, so 0 to pi. Then integrating, suppose it is a voltage, okay, then V d theta upon pi. Pi is timing, it is time, so 0 to pi, so we have written here as a pi. Okay, so we know V is equal to Vm sin omega t. Here omega t can be also be written as theta. Okay, so we wrote here theta, Vm sin theta. Then according to the formula, integration 0 to pi Vm sin theta divided by pi. Okay, then removing Vm as a constant, Vm is a constant, so removing Vm and pi out of the integration, we get 0 to pi sin theta. Then Vm by pi, integration of sine is minus cos theta pi 0. So here we can write Vm upon pi into minus cos pi, this limit cos pi minus of minus cos 0. Okay, that is Vm upon pi minus cos pi plus cos 0. So we get Vm upon pi into cos pi is minus 1, so minus of minus 1 plus cos 0 is 1, so we get Vm upon pi into 2, that is 2 Vm by pi. So average value for this first half wave, positive half wave, is 2 Vm upon pi. Okay, suppose Vm is 5 volt. Okay, maximum voltage is 5 volt. Okay, then we will get V average is equal to 2 into 5 divided by 3.14, 10 by 3.14. So in this way we can calculate the average value. But here problem with average value is that when we calculate for one half cycle, okay, when we calculate for first half cycle, we get 2 Vm by pi. But when we take another half cycle, its value becomes 0. How its value becomes 0? Let's see. Suppose limits are from 0 to 2 pi, means we are calculating for time interval of 0 to 2 pi we are calculating. We are taking this full wave. First we took half wave, now we are taking this full wave. So so v average will be 0 to 2 pi v d theta by time. Time means here 0 to 2 pi, 0 to 2 pi. Okay, now substituting for value of v, that is vm sin theta, we get 0 to 2 pi vm sin theta divided by 2 pi, that is vm by 2 pi outside, then 0 to 2 pi sin theta. Solving it, we get vm upon 2 pi. Okay, integration of sine is minus cos theta, 2 pi to 0, vm upon 2 pi minus cos 2 pi minus cos 0. Okay, so vm by 2 pi minus cos 2 pi is 1, so minus 1, this minus minus become plus, and cos 0 is 1, so we get answer vm by 2 pi into 0. So whole term will be 0, that is v average will be 0 for interval of 0 to 2 pi when we consider this full wave. Why? Because this point and this point will cancel in each other. We are averaging it, means we are adding this and then dividing it by 2. Okay, we are taking the mean of it. So this is positive and this is negative. We are adding it and dividing it by 2, so we will get 0 answer. Okay, this happens in the case of averaging. This happens in the case of averaging. In symmetric wave, this is symmetric wave. If we are taking 5 volt up here, then it will be minus 5 volt over here. In such type of case, means when waveform is symmetric, that time we will get v average as 0. This is the biggest disadvantage of averaging. In this symmetric waveform, in averaging, we are getting only value for a half cycle. When we consider a full cycle in this symmetric form, we will get the average value as 0. But how this can be possible practically? If you try to touch, means if we put two wires into the AC outlets, catch one wire with one hand and catch other wire with the other hand, we will definitely get a shock. That proves that V average is not 0. There is some voltage. So to take out the disadvantage of this averaging, we come with the word called as RMS, that is root mean square. So we will now see what is root mean square, that is RMS. There are actually 4 terms that we come across usually when we study AC fundamentals, that is peak voltage, peak to peak voltage, RMS and average values. First we will see what is peak voltage and what is peak to peak voltage. Suppose we have a waveform of AC like this. This is our time and this is voltage axis. Okay, then this point in the waveform is a peak value, that is peak voltage. If you are calculating voltage, then it is peak voltage. If we are calculating a current, then it is a peak current. It is represented as Vp, or it can be also represented as Vm, that is maximum voltage and peak voltage. It is calculated from means it is taken from 0 to this maximum point. Vp is taken from 0 to maximum point, that is our peak voltage. Now if we say peak to peak voltage, that means we have two peaks actually. This is a positive peak value and this is a negative peak value. This is positive peak value and this is negative peak value. So peak to peak means this value. This whole wave is peak voltage, peak to peak voltage. It is represented as VPP. It is represented as VPP, that is peak to peak voltage. Suppose this value, suppose this point in AC is suppose 5 volt. Okay, this is 0, this is minus V, minus 5 volt. So Vp here in this case will be 5 volt. And if we calculate peak to peak voltage, that is VPP, then it will be Vp minus of minus Vp. Okay, that means 5 volt minus of minus 5 volt, that is 10 volt. So peak to peak voltage will be 10 volt. This is a way how we calculate peak voltage and peak to peak voltage. These terms of peak voltage and peak to peak voltage is necessary when we learn RMS and average values. These two terms, RMS and average values, are very much important in studying AC fundamentals, because most of the time representation of these AC voltages are done in terms of RMS. We will learn in few minutes what is RMS and average value, but to know what is RMS and average value, this concept of peak voltage and peak to peak voltage is very much necessary. So let's now see what is RMS. RMS stands for root mean square. So why RMS is used? RMS is used to find the effective value. As we just saw now, average value is not enough to give the information about that signal, about that voltage, because in average, if there is a symmetry in waveform, then average becomes 0. To tackle it, we use word RMS. It gives the effective value of that voltage or current. So RMS voltage of an AC means here written RMS voltage of an AC produces same power and heat as that of DC. Suppose we take these two circuits. There are two bulbs, that are two loads. One circuit is excited with RMS voltage, that is AC voltage in RMS form. I will tell you what is different between that AC peak value and RMS value. I will show it, but for time being just remember that if I am giving RMS voltage, that is suppose it is a 12 volt, then as it is AC, that current will go in alternate direction. First it will go here, then it will go here. In this direction the current changes its direction alternately. But this bulb will glow and some heat will be dissipated. Okay, this is performance of a AC circuit. This is AC RMS. Now if we consider a DC, then current will flow in this direction and this bulb will glow. It will also produce the heat. But we have made RMS, that is 12 volt RMS, equal to 12 volt DC. Actually this RMS and AC RMS and DC are nothing but same in terms of power and heat dissipation. That means if we are providing this bulb 12 volt AC RMS, then it will produce same heat, same power, and it will have same brightness as that of DC, which is provided as also as a 12 volt. I am not telling that 12 volt AC is equal to 12 volt DC. No, that is wrong. But 12 volt RMS AC is equal to 12 volt DC in terms of power and heat dissipation. Now we will see how actually that RMS voltage is. We will see in waveform how it looks, how we can calculate that RMS voltage. Suppose we are having one waveform. This is AC waveform. Okay. Then I have told you previously that this point is a peak voltage, that is, or it is a maximum voltage Vm. Okay. And this point is minus Vm, that is maximum negative voltage, and that is maximum positive voltage. But actually these points are peak values, means this is a peak value, this is a peak positive value, that is Vp. But RMS value is not equal to peak value. Why? Because when we use formula for RMS, then the result we get by using that formula is less than that of Vp. Means RMS voltage will be somewhat here. RMS voltage will be here. Okay. Then VRMS. Okay. Then how to calculate it? Actually formula for calculating RMS value is VRMS is equal to Vm divided by root 2. There is a big derivation behind it. If you want that derivation, then I can put it in my description, but for a time being only this much is important. Derivation is not that important. Remember that Vrms is equal to Vm upon root 2. The way in which we derived the formula for average voltage, that in same way we can also find this formula for Vrms. Then the question arises that what will be the voltage that is coming inside our home? In our AC outlets at home, what is the voltage? Actually that voltage is RMS voltage, that is not a peak voltage. What I mean to say, that suppose in India we know the AC outlet voltage is 230 volt and 50 hertz. Okay, but this 230 volt is RMS voltage, not a peak voltage. The actual voltage of this outlet is 325, somewhat similar to 325 and 50 hertz. Now this might be confusing you, that we have learned that our AC outlet is 230 volts, the AC power that comes in our home is 230 volts, and now I am saying that it is 325 volts. How it can be? Actually formula for Vrms we know, I have written here. Okay, Vrms I have told you 230 volt. So by substituting these values in this formula, we get, if we put 230 volt, Vrms is equal to Vm upon root 2. Therefore Vm will be 230 into root 2. That will give you 325 volt. That means our maximum voltage or peak voltage is 325. So the word we use, that 230 volts coming AC, is actually, that is Vrms, not an actual voltage. Actual voltage is 325 volt. From now please remember it. Suppose if we take an example of an US. Okay, in US it is said that the outlet power is 220 volt and 60 hertz. Okay, then according to the formula vrms, according to the formula we get 120 into root 2 is equal to Vm. This will give you Vm as 169, means approximately 170 volt. Okay, that means in US you are getting 170 volt peak value and 60 hertz. Friends, but many of you might be having a doubt that in India it is 230 volt VRMS, in USA it is 120 volt VRMS. Then how the electronics appliances will work if we exchange the product between the two countries? For example, if US is manufacturing a mobile charger, okay, if US is manufacturing a mobile charger and India is buying that charger, then how it will work? Because input voltage in US is 120 volt and input voltage in India is 230 volt, then technically it should not work, right? But actually that is not the case. Whenever you buy any electronic product, it is manufactured in some standard, considering some standard that it will work everywhere in the world. Means if you buy a charger made in some, suppose USA, made in USA, it will not be written on that charger that input voltage is 120 volt. They will not write like this. Instead it will be written as input voltage is 110 to 240 volts. They give this much range and 50 hertz to 60 hertz. This is a specification in which that product is made and manufactured. So if we use that product which input is from whose input we can give from 110 volt to 240 volt, it will also work in USA, it will also work in India, and it will also work in other countries whose voltage rating is in this window. Okay, so actually I have a charger to show you, but my camera's resolution is not that perfect that you all will be able to see that label. This is my charger. If you see it carefully, if you pause the video and zoom it, then you will see that input AC is 110 to 240 volt. It is giving 0.15 ampere and 50 hertz to 60 hertz. This is the input voltage rating. It is given as 110 to 240 volts. I will put the pic of this charger in my description box so that you can see it clearly. You can also verify on your household products. You can see your charger, your laptop chargers, in any electronics appliances that works on 230 volts. You can verify it. You can see its label. It will be written as 110 to 240 volts. So if that device, if that electronic appliance is made in US, then it is not that it will only be written as 120 volt input AC. It will not be written only 120 volt. And if suppose that electronic product is made in India, then it will not be only written as 230 volt input. It is always written in range, that is 110 to 240 volts and 50 hertz to 60 hertz, because in India it is 50 hertz, in US it is 60 hertz. So friends, this was all about AC fundamentals, all the concepts related to AC. In our previous video we saw all the concepts related to DC, that is what is voltage, what is current, what is the direction of current, and all the concept related to DC. In this video we saw all the concept related to AC, that are what is the difference between DC and AC, then what is frequency, then how mathematically voltage and current is represented in AC, and then we saw some basic concepts of peak voltage, peak to peak voltage, then RMS voltage and RMS current, and average voltage, average current. We saw all that stuff. So now, so till now we know DC and AC. Now in my next video we will see how that AC is generated. It will be a small video, but your concept will be clear. It will show that how AC is generated, because in DC it is very simple that there is cathode, anode, some electrochemical reaction happens and current flows through the wires, pass through the loads. But in AC the waveform is like this. What makes that waveform alternative? What makes that waveform first go positive, then go negative and repeat itself? There might be something behind it that is making that signal positive and making this signal negative, and there might be something in DC that it is making the voltage constant. So what are that concepts? That we will learn in our next video. Thank you friends for watching my video. If you really like that video, then please subscribe my channel and please like the video. It will boost me to make more videos in future. Thank you.